So, game theory is analysis of interaction, and it originally was considered to be only that we study strategic interactions, so that when you have thinking entities, usually people who think what they want to do in order to get something, and they also were considered to be rational, completely rational, so they do the best possible given the information they possess. Now, they were not always considered to be omniscient, so they were not always considered to be know-all, but they were always perfectly rational. Nowadays, however, we study many interactions. We also can study evolution, so when the players are basically different species or different behaviors even in one species, and that behavior which is more efficient, which provides a higher fitness, that behavior managed to increase, and the behaviors which provide less fitness, they decrease, and thereby naturally those different behaviors have this dynamics. So there is absolutely no, at least no known will here, definitely no strategizing on the part of the species. The species can be whatever, birds or some kinds of birds or something. So if you have sparrows which behave in different ways, definitely they do not strategize. It's simply that they have interaction. That's the most important. We also can think that all this, that the interacting parts are people. Not always. That's the natural assumption, because it's customary, at least in the classical game theory, to look at rational interactions, and we want to think of ourselves as being rational. So we are not rational, definitely not, as Kahneman shows, for example, in his book Thinking Fast and Slow, which I recommend. So we are not very rational, but in the first approximation we are definitely rational, so that we often look on the players as being human-like, definitely rational. But again, the real game theory now is much broader. Not all participants are human. Even in our course we are going to see examples where not all participants are human. But at least we are going to assume rationality. In reality, humans and other players can be not completely rational, they can be so-called boundedly rational, let alone that they don't necessarily know all the necessary information, and so on and so forth. So in general, game theory is analysis of any interaction. Now, history is indeed quite rich, because first of all, interaction itself has been for quite some time. So, because interactive processes have been going on Earth for at least 3.5 billion years. I think there was a recent breakthrough about the emergence of life, and since you can consider life interacting, not strategically of course, like bacteria and such, but they were definitely interacting. So you can say that at least 3.5 billion years there has been going some interaction on Earth. Now, that still is not theory. That's the subject of our theory. The theory itself, of course, is less old. So it first of all has to be, for what we know, people who think of that. And if you look at the ancients, so you can say that in the Bible you have that story of King Solomon, who makes this mechanism which forces or motivates those two allegedly two women who were allegedly the biological mother of a baby. That mechanism motivates them to tell the truth, who is the actual mother, or at least to behave such that he would be able to defer that, to confer that. And there is a very nice spin-off on that, a lecture for those who understand Polish by Wojciech Załuski, extremely nice. He really gives a more contemporary, less naive view on that. And there is also a work, actually a very deep work by Uman about some Talmud problem. So that's some problem which relates to fair division, how to divide something. And he looked at a given rule, and he basically found a contemporary mathematical model which shortly describes the rule, and also, of course, that basically provides some important insights into why that rule was given. So it's important to understand what the ancients thought people should do, even though they formulated things differently from how we formulate them now. Ancient Chinese also famously thought of the art of strategic fighting. So there is this famous The Art of War book by Sun Tzu, and that is definitely a piece of game theoretic thought. And I somehow suspect that in many forms the art of war had been even before Sun Tzu. Maybe less formal and so on, but definitely the art of war had been before him, and the rules how to divide something between two people had been before Talmud. So all those rules are simply the ancient or the most ancient evidence we know, but it is probably not the most ancient thought on this topic. Now, modern game theory, that's what we're going to deal with, started, we can say, with de Condorcet, which has a statue in front of the French Academy of Sciences. So he was definitely deemed to be one of the most important French scientists, and given how many great scientists France had and has, that says something. So he, in the context of the French Revolution, he studied voting, and then also look at Cournot, who studied economical models of production. But I think he didn't gain any statue in front of the Academy of Sciences. But anyway, it was also a very important model. And then that was all formally not called game theory. So one was about voting, another one was about economics and production. But the modern, more abstract approach to game theory was actually in the 20th century. The founding fathers were von Neumann and Morgenstern. Well, von Neumann was one of the greatest, if not the greatest, scientists of the 20th century. So you've surely heard of him. Morgenstern and von Neumann, they dealt with strategic interaction, most famously, I think, with zero-sum games, which we are going to study also during this semester. And they also laid the basis for the utility theory, which studies what people want. It kind of postulates what people want. It's very beautiful and very natural. Unfortunately, that's not usually the case, or let's say so, that's not always the case. That's definitely what till now people often assume in studies, and that's the model we are going to use, so I'm going to represent it briefly. There were other great scientists like Arrow, who came from economics, also studied, there is this famous Arrow theorem, Arrow impossibility theorem about voting, Nash, which is famous stability concept, which of course we are going to study, net and Nash equilibrium, Herbert Simon, with bound rationality and other economical ideas. So I think all those guys are, by the way, novelists, besides, all those from the 20th century, besides maybe von Neumann Morgenstern, but of course von Neumann doesn't need any additional prize to be great, and Morgenstern, I'm not sure. Anyway, those are great people, and only a few I cannot put all the great scientists which contributed to that area. So that's the very rough, like plain flight view on game theory history. And now let us look at the domains of game theory. First of all, we can look at game theory as the interaction between several parties which act somehow. So since actions can be thought, at least sometimes, as algorithms, we can say that game theory is basically a multi-algorithmization. So you have several algorithms who act one with, against, or with the other one. By the way, in game theory there is also this study of what can be said when you have very bounded so-called finite automata with a bounded finite and bounded number of states who play the game. Of course, we are not going to delve into that in the course, but it's simply something which is a nice view on the topic. So multi-algorithmization. So when you have several algorithms who interact with one another. Now when these are not just algorithms, like let's say very simple animals, I don't know, bacteria, they act according to some whatever algorithm. When they have enough of whatever forage they need, they don't produce something, or they produce something. That's the algorithm. Now when the agents have some decision power, not necessarily even fully rational, but something which can be said to be decision, then we can also look at this as multi-decision theory. So when we have multiple decision makers, and again there is decision theory, so game theory is kind of a little bit of built on this decision theory, and that's also a nice way to look at game theory. So it's really something which is based on what people want. So that's something from psychology even. Definitely Kahneman in his famous book writes about psychology, and there is this then economical behavioral economics, how people behave, and of course then it can be used in basically in economics, in military, in the politics, in many other domains. So it's definitely a very interconnected domain. Now, the two main avenues of game theory are, one is game theory per se. So, given a certain interaction which we somehow formally describe, we would like to analyze what is going to unravel, what is going to uncurl there. It's not necessarily going to actually unravel. It can be like convergent to something, but I mean what is going to happen. And the second idea is, you may say, colloquially speaking, it's dual. So it's mechanism design and implementation theory. So instead of looking at a given at a given situation and predicting what is going to happen, we can look at what we would like to happen and design a situation which will motivate the participants to do what they want. For example, we can design the right auction which will motivate people to actually bid according to if they actually are willing to pay. And those are called mechanism design or implementation theory. So mechanism design mostly studies which condition can motivate a desired behavior, when also the behavior, we are basically studying how can we motivate behavior which we also are looking for. So we look, okay, this behavior is desirable because this optimizes what people get. Now how can we motivate that? So for example, it's desirable for society, let's say, that people vote honestly and don't vote for someone whom they don't like because they are afraid that otherwise their votes will be lost. That's something we look at as desirable. And then the question is, how can we motivate people to do that? That's mechanism design. So the laws, the rules are the mechanism, and the implementation theory is similar, but it's more mathematical. It says, okay, which possible spectrum of behaviors can be motivated? So what are all the possible equilibria which we can get? And again, we will of course study later what we exactly mean by equilibria. Something stable. So which possible stable states can we get? Can we make people do? Can we get as so which possible outcomes can we get? Let's say which possible, in that example, which possible voting behavior can we get as outcomes of people who are rational? That's anyhow, that's not something we're going to do here on this course. So just something which we need to know that exists. So there exists this dual engineering endeavor. And let us now look at the sub-disciplines of game theory. So it can be broadly looked at as consisting of two parts. One is non-cooperative game theory and the other one is cooperative game theory. So the cooperative game theory studies possible coalitions as the basic building block of the situation of interaction. And non-cooperative game theory studies possible actions. So for me, for example, non-cooperative game theory is more natural as the basic theory. And it's so for many people, but still some people say no, we don't think it's natural. So for example, Rubinstein and Osborne, in one of the books I recommend, which is called, I think, A Course in Game Theory, they actually say that they don't think that one of those theories is more basic than the other one. That's a matter of taste. What we need to know is that there are two theories. One looks at the actions of the agent as a basic building block, and they ask what they're going to do and such. The other ask at what are the coalitions which are going to be formed, and how are they going to divide their utility, their revenue in those coalitions. That's the cooperative game theory. Okay. Now, non-cooperative game theory in turn divides into two major avenues. One is dynamic. When you look at how the process unfolds in time, so a participant does this, another participant does that, and so on and so forth. So I look at what the other person did, and then I decide what I do. That is dynamic, often modeled with extensive games. And the other one is static, often modeled with normal games, normal form of strategic form, that's the same. Static is more abstract. So all this course of action, so I do this, and if the other guy does this, then I do that. All this is called a strategy. So all this contingency plan is called a strategy, and then I look what will happen if I choose that of this strategy. So that's a more abstract, more, in a way, it's a simpler model. It does not allow to look into those dynamic interaction, like what I remember and what I know and what I see from the other guy, but it does allow to concentrate on the properties which follow only from those strategies. So like basic stability concept of strategies and so on. Now, the non-cooperative games can be also divided into classes. For example, this is not an exhaustive list, so the examples are by utility. So when the players have in a certain way a common goal, not exactly the same, but they in a way they align, then it's called the potential game. That common goal is called the potential. When the players are opposed, exactly the opposite, then it's called the zero-sum game, constant sum general. So that the total utility is constant, so whatever I get is what the other player loses, and so on. That's exactly the opposite in a way of this potential. And so we can, for example, speak about that. Now another way to divide games is by strategy set. So basically, usually, and we are going to define a game to be finite if all the strategy sets are finite. So for any player, there is only a finite number of options that player can choose from. So mostly, not always, but we are going to mostly look at such games, but not always. Sometimes it's interesting to model what happens if a player can choose any real number from some interval. And in some cases, it is a reasonable model. For example, when you shoot and you choose the angle, it can be reasonably modeled as a real, or at least as a rational number, and so on. Now, another option is, for example, in the infinite games, the question whether whether there exists a player who can always win regardless what the other player does, or whether both players can get a draw at least. Such questions, I'm not going to go into details, but such questions are not always even formally completely known. That's related to the so-called axiom of choice. And there is this famous axiom of determinacy. We are not going to get into that here. I'm just going to mention that it exists. In some cases, it's important to distinguish that. We are not going to do that here. Okay. Now, cooperative games. So before we have been looking at the classes of non-cooperative games. Now, cooperative games. Now we are going to explain them. Can represent the value of each coalition. That's the basic of the definition of a cooperative game, either as a so-called characteristic function, which is basically a function which assigns a value to each coalition. So I know that if I join Jane and Max, then we are able to achieve that. It can model political power, or on a market it can model production power, or something else. Or we also can represent the values of coalitions by a set of rules, and that's often more efficient. So there are different ways to represent the values of coalition. And the classes of cooperative games also can be looked at. For example, this is not an exhaustive list, but that's just a nice thing to have a first taste of that. So by whether we are able to divide the value of the coalition, so whether we are able to arbitrarily divide the value of the coalition. So if, let's say, we get some money from whatever we produce, then it's natural to model that as a game where we are able to arbitrarily divide this gained value, which is called transferable utility. So we can transfer the utility we gain anyhow. But however, if we are able to get some political achievements, that's already not clear whether we are able to arbitrarily at least divide that between us, because I may basically have some political goals which are not satisfied by some political achievement which our coalition can fight for. We are going to, hope we have time, go into games with only transferable utility. That's I think simpler, and that's definitely simpler. That's what we are going to do. And then also the value function, so the function which defines what is the value of each coalition, can be subadditive, superadditive, and so on. Now I just can. That's not something we are going to delve into now. This is something for later, but very briefly, subadditivity means submodularity. This function can be submodular. I didn't mention it here, but submodularity, for example, that's a natural, often real property that adding something to a larger set gets you less addition, less marginal value than adding something to a smaller set. So if you don't have any food yet, you will enjoy yet another apple much more than if you have already 5 apples and 3 pears. And subadditivity means simply that the value of a union of coalitions is at most the sum of their values. Again, that's an important thing to know in general. That's very useful in computer science, in theoretical computer science, but that's not something we are going to go into right now. I'm just trying to give you a general flavor of that. And now again, let us go and see the general flavor of this mechanism design versus implementation theory. So mechanism design designs the game that would motivate certain behavior. For example, that people bid honestly, that people vote without manipulating, without voting for someone they don't really want because they know that their most preferable candidate will not have enough votes. So when we want to motivate certain behavior, which we consider as good, so for example, that people bid honestly, and that we also, for example, in the case of an auction, maximize the social good, so that we provide the item to the person who really values that the most, given that we have managed to motivate them to tell the truth about their value. Or in the case of an auction, we also sometimes want to motivate the revenue, which is typically hard, but it's also an important question. The revenue of the auctioneer. So if you want to sell something on eBay, that can be a nice example of such things. And we are not going to do this here, I think, or maybe we'll have a couple of examples. It's definitely a topic I recommend. So there are very nice lectures by Ralph Gardner on the net, and I would definitely recommend watching more and reading more on that. Now, so mechanism design is quite practical. Now, implementation theory, on the other hand, it's similar, but it's a bit more mathematically more formal. So it says basically which behaviors can be motivated. What are all possible behaviors which you can motivate people to do? What is the set of possible behaviors? So it's a more mathematical question. So that's very close. It's not important to delve into the distinction now, but it's important to understand that. And there are also several other related topics related to game theory. So we mentioned that there is game theory, most famously cooperative and non-cooperative, and there is mechanism design and implementation theory as a dual business. So now there are some related theories to game theory, areas to game theory. For example, epistemic game theory concentrates on knowledge, what we know, what we can know, what we believe in, how I believe change, and all these things. So epistemology is what we can know, and that's definitely crucial for decision making. And epistemic game theory concentrates on that. Logic also, we can model stuff using logic, and we can model game theoretic notions using logic, for example. There are very nice works on that. And also algorithmic game theory, that's something which studies the interplay of algorithms with game theory. Now it can be many multifaceted. So first of all, algorithms can define games. In the sense that I can say that, okay, assume that the players are actually playing according to some given algorithm, and we would like to see who can provide the best player within the given size of the software or number of states of the automaton which plays. So that's a so-called machine game by Debreu and Rubinstein. We are not going to delve into that, but that's a very important topic. Another topic is the other direction. So not algorithms defining games, but games giving rise to algorithmic questions. So studying games algorithmically. For example, finding the stable states. After defining, let's say, the mesh equilibria, we want to ask, so can we find one? Can we find all of them? And generally that's known to be a very hard question, and that's a very, very beautiful and highly non-trivial topic. So that's another question. And evolutionary game theory also can be looked at algorithmically. So calculate the outcome of some dynamic. So there are many, many questions in the interaction of algorithms and game theory. In general, I'm a person of computer science with economics, or let's say computer science with game theory, and especially with the advance of the internet, the intersection has been gaining a lot of importance. So that's definitely a very important prolific area. We are going to mostly study pure game theory, but we are going to sometimes talk about algorithmic aspects. Now, application domains of game theory are very broad. For example, non-cooperative game theory can model military interactions, monetary investments. So we decide how to invest, we decide what to produce, evolution. There are models which describe why the human society is as is, why the other species are as they are, and so on. There are many, many interesting models in that area, and many models to study. Now, cooperative game theory, naturally because of the coalitionary questions, models political games. It can also model markets. It can model how we should divide profit and cost of interaction based on which coalitions, let's say, of producers, of consumers could be formed and what they could gain. So there is a very classical paper from the 70s which models dividing the cost for the runway for planes, for airplanes, based on coalitionary game theory. It's a very beautiful paper. It's not so hard even, but it's a very nice application of that theory. And written here, team forming. So we sometimes just want to predict which team is going to be formed. And if you think that the details of transformation are less important or unknown, we may model this using cooperative game theory. And for example, Agis Elkin does beautiful work on that. Now, mechanism design has applications in preference aggregation, so deciding something based on the preferences of several people. For example, most famously it's voting, of course. So what is the mechanism, what is the way we organize voting, such that people will vote to the actual candidate and such that the candidate is going to satisfy them and so on and so forth. That's not trivial. You often think of some way of just choosing the one who gets the most vote. But that's very amenable, very much, liable to manipulation by the people. So we don't necessarily want that rule. So voting, legislation, so which rules, which laws will motivate the population, do what we want, and what is the right way to organize auctions. And for example, on eBay there was a story that someone wanted to sell I think they wanted to sell a spleen, either a spleen or a kidney. Anyway, they want to sell an internal organ. And the price achieved some very high value before just eBay cancelled that whole auction and made a rule that you may not sell body parts on eBay. And of course we can discuss whether it's a reasonable thing. That's not really a question for game theory, that's more a question for philosophers maybe. It's an ethical question. But it's also a question to game theory, because given what we want, you may ask, how can we motivate it? And there were many stories like auctions for radio frequencies or other broadcasting frequencies that went well in the States, for example, or that were extremely wrong in certain countries. And sometimes the government had hoped to earn a lot of whatever, 5 milliards, and earned 5 millions from the auction. And sometimes even the whole idea was not exactly efficient, so maybe the company that got the frequency was not really the company who wanted it most. So auctions definitely are very practical, and also you want to ask which societal norms would we like to encourage, because we would think they are going to be efficient. Because often people say, okay, they're going to encourage something we like. For example, you want people to earn more money, so even if people are not educated, you want them to earn more money. But if you force the employees to pay at least some amount of money, then employees may say, yeah, you know what, if a person is not worth that, if I don't, as an entrepreneur, if I don't get that value from the person, I'll just not hire the person. Or I will hire another person who will do several things. Or I will close my business if it's not viable anymore. So sometimes people decide they want something, and that's a question whether it's good or bad. That's an ethical question. But even given that they want something, their implementation is often extremely wrong. So it's definitely important to understand, first of all, an evolutionary question, why certain societal norms have been formed, and the other question is, which norms shall we encourage if we want to get some behavior. Okay, so I hope I've motivated you to love game theory, and yet one thing is that there are several approaches, normative and descriptive. So we are going to take a normative approach in the sense that we are going to, not in the sense of societal norms, but in the sense in the sense of we are going to say what should be done, what should, assuming certain properties. Assuming everybody is rational, that's how they should behave. That's what should be according to some rules. Not necessarily very practical, but very good for the beginning. Now, the more practical, arguably, or at least the also interesting descriptive view, what people actually do, given all human imperfection or all human beauty or whatever you call it, will inspire our model. But once having the model, we are going to let it free just for math. We are not going to always, of course, be exactly as real life is, which is always impossible in science, but in the introductory course we are going to do this extremely normatively. Now, okay, in the next lecture we are going to talk about one of the basic theories which underlies game theory and is closely related to the motivation people have, or in general players have, that's utility theory.